Okay, this video is for calculus, talking about, well, we call them derivative shortcuts, but they're really theorems about derivatives that allow us to compute derivatives more quickly than using the limit definition of the derivative. That's the least favorite way to calculate a derivative because it takes so much really detailed calculations. So we use these things that we just call shortcuts. And there's kind of two classes of them. One is there's the theorems that talk about the derivatives of individual functions based on function type. And then there are a series of what we call derivative properties, which allow us to combine those in different ways. All right, so let's go ahead and take a look. The limit definition of the derivative is the official way to determine a derivative equation for a given function, but it is very time consuming. So to accelerate finding derivatives that we're going to focus on later, where we just want to be able to take the derivative quickly because we're going to use the derivative, we need some ways to calculate derivatives more rapidly. And these will typically calculate the derivative at any value x rather than a pre-plugged in value. Just as an example, let me show you a derivation. Now, this section in the notes, I'm going to pause on each of these screens so that you can take a closer look if you would like. But for the most part, we're not going to go through all the proofs. Let's say, though, that we'll show you a couple of them. Let's say that we have this. We have a function f of x is just a constant, any constant c, like 10 or 0 or 15 or 3,000, something like that. What would the derivative of that constant be? Well, if we did the limit definition, we would say the limit as h approaches 0 of f of x plus h minus f of x change in y over change in x, which is h, as the change in x goes to 0, is defined as the limit definition of the derivative of the function f. And then what we would do is take our two copies of this function, and we would plug in x plus h into the function. Now, since there's no x here, we would be the function would just remain the constant. It would also be the same constant here. That minus itself is a 0, so that is a 0 over h, which is just a 0. And since there's no place to plug in the h, this limit is effectively 0. Okay, so we're going to summarize that result. It's a theorem that says that the derivative of any constant is equal to 0. Now, this structure right here is called the derivative operator. It's like other operators that we've seen. So, for example, we know about the square root operator, right? The square root operator says return a number where if I were to take that same number and multiply it by itself, I would get the result. So, or the input to this operator. So the square root of 4 is 2, right? And then when we use that operator, that square root operator, we replace this with the result, and that means that the input and the operation all gets consumed, producing the output result. Right? So that you can think of this as the square root operator. Okay. This operator means to take the derivative of whatever is inside and replace all of that with the result of the derivative. So I could write this. I could say the derivative of 15, since it's a constant, is equal to 0. Right? This is another way to say take the derivative of. It's called the derivative operator. And we call d dx. This indicates what the variable is that we're treating as the x variable or the independent variable. All right, so here's a little proof that shows that. Now that we've done this proof, we never really have to do that proof again. We just know that anytime we take the derivative of a constant, it's always 0. All right, here's another one that's quite a bit more involved. Let's say that we have f of x is x raised to any power n, right, except for 0, because x to the 0 would be 1, typically, although 0 to the 0 is another matter. But as long as n is anything other than 0, we could definitely use this rule. So let's go ahead and evaluate that. If I use the limit definition, we would be plugging x plus h into this function. So this is x plus h to the n in this copy, minus just x to the n here. And then we can't evaluate by plugging a 0 in because that would be divided by 0, but we hope if we expand this all out with algebra that we can factor out and cancel that h somehow. And you can factor this, or you can expand this x plus h to the n power using the binomial theorem. There's a structure to be able to do this. This is another way to say combination. So this is equivalent to saying n choose 2, n choose 3, and so on. Okay. And then minus x to the n. And then what happens is this x to the n cancels the very first term, But that leaves a whole series of remaining terms, all of which have an h, at least one h in them, which means you can factor out that h, and then that h can be canceled, which means now you can effectively plug the 0 in. And when you plug the 0 in for h, right, that makes this term, which has an h, go to 0, this goes to 0. All these terms here end up canceling out, and you're left with only this first term, which is n times x to the n minus 1. All right, so we're going to summarize this result. This is sometimes called the power rule. When you have x raised to a power and you take the derivative, you simply take the power, the exponent, bring it down as a multiplier, and subtract 1 from the exponent. Let me give you a couple quick examples. Let's say that you wanted to find the derivative of x to the 4th. Right? Well, that means you bring the 4 down as a multiplier, and this becomes x to the 3rd. So instead of having to do this whole big limit thing, we just do it that way. And this works for non-integer values too. Let's say that you have the derivative of x to the, well, let's make it like negative 1/2. Let's say something like that. That means you would bring the negative 1/2 down, negative 1/2, x to the negative 1/2 minus another 1 would be negative 1/2, which is negative 3/2 power. Right, so you can use this rule with non-integer n's. It's fine to use that with any power. Right, so that's called the power rule sometimes, and that's the second of our shortcuts. The derivative of a constant is 0, and the derivative of x to the n is x times, or n times x to the n minus 1. We will eventually memorize all of these things, so get used to the idea that you'll have to memorize them. Now, I'm not going to go through the rest of the proofs, but they're all in here. I'll show them really quickly in case you want to like pause the video. Here's the first half of this, or here's this proof. The first half looks like that. There's a definition that the letter E is this particular limit. You can do a substitution. So pause the video and look again at that if you'd like to see that in more detail, but we're just going to note the result. The derivative of E, specifically E, which is the number 2.718, it's like pi, it goes on forever. E to the x, the derivative of that is an exact copy of itself. It's the only function whose derivative is an exact copy of the original input function. Okay, what about this? The derivative of sine turns out to be, I'll show you the proof real quickly. You can read through it in more detail. Here's the beginning of the proof. In the middle of the proof involving a trig identity. And the conclusion of the proof. So that proof shows that the derivative of sine of x is equal to the cosine of x. Another thing we'll need to do. In fact, I'm going to summarize. All of these are provable. The derivative of a constant is 0. The derivative of x to the n is n times x to the n minus 1, power rule. The derivative of e to the x is just a copy e to the x. Any other base, like for example, the derivative of, let's say, 2 to the x, is also a copy 2 to the x, but you have to multiply by the natural log of that base. So there's an extra multiplier of the natural log of that base. The derivative of sine is cosine, and it turns out that the derivative of cosine is negative sine. So here's the first four what we call derivative shortcuts. They're really the theorems for determining the derivatives of particular function families. Okay, now we're going to look at what we call I call them the properties or the rules. So they're also provable. Let's say that you have the derivative of a constant times some other function. So let's say we already know how to handle the derivative of x squared, and we know that that's 2x now. Bring the 2 down, subtract 1. What would the derivative of 4 times x squared be? Well, if you have a constant, what we do the limit definition here, you can take that constant times function plus x plus h in, and then constant times function. When you factor out the constant, you end up getting that since this constant is unaffected by this h going to 0, you can bring it outside of the entire limit. And this is just the derivative of the function itself. So it turns out that the derivative of a constant times a function is simply the constant times the derivative of the function. Its official name is the constant multiple rule, but what I just think of it as is constants can move inside or outside of derivatives. You can just simply move that out. So the way I would do this is I would simply move this 4 outside of the derivative, and then I would apply the power rule there, that derivative is 2x, and get 8x as the result. Okay, so that's the first property. Next one is the sum of two functions. So let's say that we have a function and another function, or you can think of it as two terms. You would use this, for example, if you had this. Let's say you had x cubed plus 5x to the 7th. You can think of each of these terms as its own function. So it turns out, if you go through the proof, I'm not going to go through the whole thing, but you can see it here, that the derivative of one term plus another term is you can take the derivative of each term separately and then just combine them by adding. Which means that if I wanted to do this, I could say this property, which is called the summation rule, is I can take the derivative of x cubed and the derivative of the 5x to the 7th separately and add their results. And then finally, I can take this 5 outside on this one, so that I get that the derivative here is 3x squared plus 5 times the derivative of 7x to the 6th, or 3x squared plus 35 times x to the 6th. That would be the result. All right, so that's the sum rule. There is also a difference rule. If the terms are separated by a subtraction operation, you just take the derivative of each term separately and subtract the results. So that's what allows us to do multiple terms, just term by term. So we're going to do just a few quick examples here. I think we've got about 5 examples, and then so these first ones are real, I would say, very common, and then these last 2 examples here are a little more esoteric. So let's see how far we can get here. So first, you can pause the video and try these on your own, and then unpause and see if you get them right. I'm going to go through them pretty quickly here. So let's say we have f of x as x to the 5th. I'm going to use the power rule. Then I'm going to label the result f prime of x. And I'm just applying this. I'll actually show you one more thing with the notation. F prime of x is equal to the derivative operation done on x to the 5th. Right? But what I would usually just do is directly go to this step and say the derivative of f is called f prime. And the result is I bring the 5 down and I subtract 1 from the exponent to make it 5x to the 4th. This is the answer. Okay, and then this one, we're going to do the same thing. F prime of x, we're going to bring the 2/3 down as a multiplier. And then we have x and then 2/3. So what is 2/3 minus 1? 2/3 minus 3/3 is a total of negative 1/3. So that would be this. Okay. All right, and then the third one, g of t, so now the independent variable is t. So we don't have a rule for handling something on the bottom here, but by exponent rules, if I move this t to the 5th to the top of the fraction, that's the same as 2t to the 5th over 1, or just 2t to the 5th, right? Whenever you move a base to a power to the other side of a fraction, it changes the exponent sign. Sorry, this would become negative 5. So positive 5 exponent on the bottom becomes a negative 5 exponent on the top. And then I can apply the derivative, right? The power rule derivative means we would bring the negative 5, it would join the 2 down there. So that's going to give me negative 10 t to the, now you got to be careful here, we subtract 1 so this gets more negative and becomes that. And if you want to practice simplifying, maybe try to put it back in the original form where we only use positive exponents. That's equivalent to negative 10 over t to the 6th. Okay, again, you can pause these videos, try the problem on your own, and then unpause. All right, now here's one where you have separate terms here. I'm going to treat those as if they're separate functions, but I'm just going to label the result f prime of x. Power rule here, so that's going to be, it's really 3 times, I'll show this, 3 times 5x to the 4th. This is a 4 times the derivative of that, which is an exact copy. And this is a constant, so its derivative is 0. So you could write it like that, and you're not required to simplify, at least not in AP calculus. So you could write it that way, or if we wanted to simplify a little bit, we could multiply those together and then just drop the 0 term altogether. Okay, what about this one? So we don't have a quotient yet, although there is something called a quotient rule that we'll cover later. But instead, I do have a common denominator here. So let me just note something. If you have something like, let's say we had 2x over x to the fourth minus 3x squared, that is not equal to 2x over x to the fourth minus 2x over 3x squared. You can't do that. That is not allowed. There's no such thing as a common numerator. But this is a common denominator, which means you can split it this way. So I'm going to label this g of x just to indicate I'm still just rearranging this or simplifying it. I'm going to write that as x to the fourth over the common denominator 2x minus 3x squared over 2x. So it is legal to split the numerator up and put each part of it over the common denominator, but it is not legal to do the same with a common numerator. Okay, now there's more simplification we can do here. So I'm going to still say this is g of x. This is x to the fourth on the top and x 1 on the bottom, which means the total is x to the 4 minus 1, which is x cubed. And then I'm going to write this 1 over 2 separately as a fraction 1. Similarly, I'm going to take this 3 over 2 and write that as a multiplying fraction. And then this is x squared divided by x, which is an x. Well, so far we have not taken the derivative. Right, we're just doing algebraic manipulation to simplify this into a form where we have multiple terms. In each one, we can use one of the shortcuts for them. So now I'm going to write this as x prime of, or g prime of x to indicate I'm taking the derivative. And then I've got the 1/2 multiplier, 3x squared. And I've got this. Now, let's talk about this term. Okay, there's a couple ways to think about this. What is the derivative of 3/2 x? Well, first, you could say that that is equal to 3/2 times the derivative of x. I'm going to write that as x to the first power. Right? So if I do the power rule here, that would be 3/2. This would be 1 times x to the 0 if I subtract 1 from that. But x to the 0 is 1, so that means this is 3/2 times 1 times 1, which is just 3/2. So you can do the power rule in order to do this term. You can think of this as x to the first. But I actually think of this a little bit differently. The way I think of this, taking the derivative of 3/2 x, is I think, hey, if this was y equals 3/2 x, that would be a line, right? Equation of a line. And this would be the slope of that line. And since I know that the derivative of a function represents its slope, then that means for all x's, this line, this whole term, has a slope of 3/2, and therefore the derivative is just the 3/2. So instead of doing it this way, although it's technically correct, I would just look at that and go, oh, the slope is just this number here, 3/2. Okay? So whenever you have just x to the first power, the derivative is simply the number that's multiplying by that, because that's the slope. Okay, let's take a look at a couple more examples. Now these two are quite a bit more involved, and this first one, you could definitely see something like this on the AP test. The next one is quite a bit more involved and not very common, but this is pretty common. For what values of a and b is the line 2x plus y equals b tangent to the parabola y equals ax squared when x equals 2? Wow, a lot going on. All right. Well, the first thing we could do is say, just think about this for a second. If you have a parabola, y equals ax squared has this general form for positive a. And then at x is 2, if we wanted there to be a tangent line, this line to be tangent, then what would have to be true here? So at x is 2, the y values would have to be equal, and the derivatives would have to be equal, right? We would have to have the same y value for both the curve and the tangent line, and the slope of the line should be equal to the derivative of the curve. So let's see if we can make that true. Let's solve both of these things for y. Let's make the y's equal. Okay, well, we've got 2x plus y equals b for the line, which means that y is b minus 2x. And we have for the parabola y equals ax squared. And that means that this y has to equal this y. So ax squared must equal b minus 2x. Okay, that gives me an equation. Okay. And this has to be true at x equals 2, because that's the point of tangent c. So I'm going to plug a 2 in here. And that would give me a times 2 squared has to equal b minus 2 times 2. So that is 4a has to equal b minus 4. Okay, I can't solve for a or b, but at least I have an equation that relates the two. And that's what setting the y is equal gives me, an equation that relates a and b. Let's now look at the other thing, the derivatives. They have to be equal as well. So to make the y primes, the derivatives equal, we can take this equation of the line, which we solved already to get y is b minus 2x. And let's take the derivative. And I'm going to write that derivative as y prime. That's a constant, so its derivative is 0. And this is x to the first power, so its derivative is just the slope of negative 2. So that's y prime is negative 2 for the line. For the parabola, we have y equals ax squared. And that means that the derivative is, by the power rule, we bring the 2 down here. So it's 2a times x to the 2 minus 1, which is 1. And if these two y primes have to be equal, that means 2a times x has to equal negative 2. And that gives me a second equation, which means I have a system of equations now. 2ax must be negative 2. Well, I could even go further than that, actually, before I write this. This has to all be true at x equals 2. So that means if I plug a 2 in here, 2a times 2 has to equal negative 2, or 4a has to equal negative 2. And that's my second equation. So I have a system here that has the equation 4a is a negative 2, and 4a has to be b minus 4. So solving that as a system, I could solve this for a first. A is negative 2 over 4, which is negative 1/2. Then I can substitute that in this equation. 4 times that negative 1/2 for a has to be b minus 4. So that's going to be a negative 2 has to be b minus 4. If I add 4 to both sides, I'm going to get that 2 equals b. So it looks like the magic numbers here are is if a is negative 1/2 and b is 2, then this line and this parabola will be tangent to each other at x is 2. That you can see questions related to that on the AP exam, I would say. This last one, I'm going to just tell you right now, is pretty unusual. It just shows you kind of the limit of what you could do with this, but definitely more difficult than you would normally see, even on the AP exam. So if you want to end your video right here, you're not going to miss anything that important, but stay tuned if you want to see how crazy and powerful these derivatives can get. Let's say that you want to find a cubic function, y equals ax cubed plus bx squared plus cx plus d, whose graph has horizontal tangents at these 2 points. So what would have to be true for there to be a horizontal tangent? Well, if you had a cubic function, which in general would look like this, a horizontal tangent would be a place where the slope is 0. So that means the y prime would have to be 0 at both of those 2 locations. Right? At x is negative 2, and also at x is 2. Okay, so let's see if we can figure that out, right? We've got this y. It's ax cubed plus bx squared plus cx plus d. And I can take the derivative, since I know I'm going to have to set it equal to 0. By the power rule, that's going to be 3ax squared plus 2bx plus c, and that's the slope there, and then this is a constant derivative of 0. So if I want this to be equal to 0, the first thing is y prime has to be equal to 0 at x is negative 2. So if I plug a negative 2 in here, I have 3 times a times negative 2 squared plus 2 times b times negative 2 plus c has to be 0. And that gives me 4 times 3 is 12a. Negative 2 times 2 is negative 4b plus c has to equal 0. So there's an equation that I can put in the system. But the other thing is that I have to have this same y prime equals 0 at x is positive 2 to match this point. Okay, so we can do this y prime equals 0 at x is positive 2 by plugging a 2 in here for the x and the 1 prime. So 3 times a times 2 squared plus 2 times b times positive 2 plus c. That also has to give me a derivative of 0, so that's 4 times 3 is 12a plus this time positive 4b plus c is 0. That's my second equation. But I'm going to need more equations than that if I'm going to be able to solve for a, b, c, and d. So the other thing is not only the derivatives, but when x is equal to negative 2, y has to equal 4. Or I'm sorry, 6. So I could take the original equation and say that y must equal 6 at x is negative 2. So I'm going to plug in negative 2 into the y equation here. So that is a times negative 2 cubed plus b times negative 2 squared plus c times negative 2 plus d. And that has to equal the y coordinate there, which is 6. So that gives me negative 2 cubed, which is negative 8a. Negative 2 squared is positive 4b minus 2c plus d has to equal 6. And then I can do the same thing here. When x is 2, y has to be 0. So if I plug a positive 2 in for x here, in this equation for y, I'll get a times 2 cubed plus b times 2 squared plus c times 2 plus d. That has to produce a y of 0. And that is positive 8a plus 4b plus 2c plus d equals 0. That gives me 4 equations for these 4 unknowns. We'll change colors here and we'll do a system solution. Okay, so let me write the equations. I'm going to kind of line everything up here. I've got negative 8a plus 4b minus 2c plus d equals 6. This equation is positive 8a plus 4b plus 2c plus d equals 0. And I've got this equation, which is positive 12a minus 4b plus c plus no d's has to equal 0. And this equation, 12a plus 4b plus c has to equal 0. As a system, probably the easiest way to solve this would be to use RREF. So I'm going to take the coefficients here. Negative 8, 8, 12, 12, positive 4, negative 4, positive 4, negative 2, positive 2, 1, 1, 1, 1, 0, 0, and augment that matrix with the right-hand side numbers of 6, 0, 0, 0. And then I'm going to bring up a calculator and solve this with the RREF method. So hopefully you're familiar with this, but you can take like a TIE4. You can go to the matrix menu and edit a matrix. For example, this one is A. We're going to make this a 4 rows by 5 columns matrix, 4 by 5. And then we'll enter all these numbers using the negative key here for negatives. Negative 8, 4, negative 2, 1, and 6. Second equation, 8, 4, 2, 1, 0. The third line there is 12, negative 4, 1, 0, 0. And the last equation is positive 12, positive 4, 1, 0, 0. So once that's all entered, we can go back to the command line, back to the matrix menu, over here to math, scroll down until we get to the RREF, reduced row echelon form function, and then go back to the matrix menu and say to perform that operation on matrix A. Then I'm going to go math to fractions and get that. After we do RREF, this is how I typically ask students to show work. I'm going to smell it up for a second. So after we do RREF, we get the matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and the numbers are 3/16, 0, negative 9/4 and 3. Okay, let me go back to full screen on this. Okay, what that means is that this first column is 1a and nothing else is 3/16. So that means the a is 3/16. So I'm going to rewrite the result here. This is y is 3/16 x cubed. The b is 0, so this is 0x squares. C is negative 9/4, so negative 9/4 x, and the d is 3 plus 3. Okay, so this is the third order polynomial that goes through those 2 points and also has horizontal tangents at those 2 points. So you can do some pretty interesting things with these derivatives. All right, that concludes this lesson on the very basics shortcuts. You should steel yourself to memorize many of these shortcut rules. There are many more than these.